Hello everyone, welcome back to this YouTube channel of Geophysics by Dedalo. Today I am to show you this new paper published on the journal SoftwareX. It's about the development of a tool for a multiparametric analysis of an earthquake, searching for possible lithosphere, atmosphere, ionosphere coupling in unified research framework. You can find from the published paper the link to the GitHub repository where you can download our Jupyter Notebook virtual research environment where you will find the code to analyze data. And this code is available in Python or MATLAB kernel. You can choose the one you prefer. So I suggest you here to download the repository. We already downloaded it, and you can unzip in a folder of your computer. We already put inside this folder, and we launch the Jupyter Notebook, and now I show you what you can do with this. So you type Jupyter space lab, and then you can give the address where you unzip the SEISMO-VRE, that is the name that we gave to this tool. So this you put enter, and this one will launch a Jupyter server on local on your computer, but you can also try our SEISMO-VRE directly on GitHub. I just show you that you can find this button, Launch Binder, that will open a remote server where you can execute and even modify the SEISMO-VRE. As you see, this is loading, and so you can see what we have developed and even modify them. That is what we are going to do. But we use now the local version. This is the virtual research environment. You see there is analysis of lithosphere, atmosphere and ionosphere. But the first stuff is to collect the data. This virtual research environment provides some global variables that are the space, time and parameter of the earthquake or the natural hazard you want to analyze. In the paper you will see the example of application to Italian seismic sequence 2016, Marmara 6.2 2025 earthquake, or even in supplementary material a step-by-step guide showing how to apply this SEISMO-VRE to a volcano eruption of Mount Etna in 2015. Now we can modify this parameter to analyze a new earthquake. For example, this earthquake of magnitude 6.4 occurred on 26 November 2019 in Albania. It was quite a large earthquake with inverse focal mechanism, and now we will put this parameter inside our virtual research environment showing how to analyze this earthquake. So first of all, we get this parameter on one side of our screen. On the other side we put our Jupyter Notebook, and firstly we need to go in the subfolder data where there are two Jupyter Notebooks, one in MATLAB and the second one in Python, the one that now we are going to open. And now here are the libraries necessary to download the data and execute our virtual research environment. Now we put the parameter of the earthquake, so the year is 2019, the month of the earthquake was November, the day was 26, the earthquake time is 2:54 as a minute and 12 seconds. The epicentral coordinates, as you see, they are 41 degree north, 514. Just type this number here, and the longitude was 19 degrees, point 526. So we just type this parameter here. The earthquake magnitude was 6.4 and the depth of the earthquake were deeper than the one in Italy, 22 km deep. And fault strike we can get from the moment tensor solution. From the nodal plane we get 156 degrees of the orientation of the fault responsible of this earthquake. Was quite similar, is just the case. Here is set that to analyze 8 months before the earthquake and 0 days after the earthquake. We can leave, but you can change and see how the result would change, changing this parameter. After filling the earthquake parameter, you just run this cell, and now this parameters are loaded, so the data are downloaded from this earthquake. You need to download the atmospheric data, but this one will require a lot of time, so we already downloaded before and we put in the proper folder. So this one can require about 15-20 hours or even more than 1 day, so you need to wait quite time. But if you go in the beginning, you can find a link directly to the ionospheric data. This one is from Swarm satellite. You just execute and now ask the token. So you can just press enter or go here. If you don't have, you can log in the, or register, is free in the virus Swarm with the Earth observation account. Here I already registered, so I log in. I can create a new token and I just copy and paste this inside this VRE, press enter, and then now the VRE is downloading the satellite swarm data, and this one as you see, it is very quick to download the data, and after downloading the data, it extracts the tracks, the satellite tracks, inside the research area, that is the Dobrovolsky area, and as you see, it's processing the downloaded data and saving the tracks. And now it's for Swarm Satellite Alpha, and then it will proceed for also Satellite Bravo and Satellite Charlie. And as you see, this is the list of all Swarm track that have been automatically saved. And now it will proceed for Satellite Bravo and then for Satellite Charlie. Now we can go back to full screen and just wait a bit for the complete that this task will end. And now processing is complete and saved 716 files. So we now have all the data that we need. So we can go back to the main folder. In this notebook, and we need to put the same global parameter also in the main notebook. This is very much important. Otherwise, we cannot analyze the proper earthquake. We get the earthquake time, earthquake location, of the epicenter, the magnitude, the hypocentral depth, fault strike, even day before and day after if you change, in this case not. We copy, Ctrl-C, and then paste in the main folder with Ctrl-V. And so now you see they are the parameter of the Albania 2019 earthquake. We can now do edit clear output of all cells. So in this way we removed the output from the Italian seismic sequence and we don't confuse. And then we can just type run all cells, or if there are some issues you can run also specific sections of the code. And now the code is running. It required just a few minutes. As you see, it already ran the global variable to acquire which parameter we want to analyze. Now it's connecting to the EPOS, European Plate Observing System portal to download the earthquake catalog. This one it's downloaded on the main and it's updated in quasi-real time on EPOS, so you can found the also the earthquake that are occurred in a few time ago. For atmospheric data, they are updated one time a month, about in the half of the next month, so you cannot analyze the earthquake occurred before 1.5 2 months, depends on the day of the earthquake. For swarm satellite data, they are updated with a delay of about 3 days for this swarm product, that is the operational product from swarm, but there is the possibility, if you want to run in real time, to change the product and use the fast data that are provided more time in the same days, as long as the data are downloaded from the satellite and processed. So now it's collecting all the data from the earthquake catalog connected from EPOS, and this need to arrive to the day of the earthquake, because we asked from 8 months before up to the day of the earthquake, that was in November, so this one requires a bit of time. Okay, now is downloading the last day of November, now the last query, and we can now see this is the earthquake map of all downloaded earthquake. Then we are going to analyze only the earthquake inside the green circle, that is Dobrovolsky radius, and it is automatically done by the virtual research environment. So you want to change the radius of analysis, you can change the code because it's open source. Then the virtual research environment shows the trend of the number of earthquakes over time. There are sometimes with a little more earthquakes inside the Dobrovolsky area. And here is the cumulative Benioff strain, so the square root of the released energy by each earthquake. Then is calculated the ES parameter, the daily energy released by each earthquake, divided for the square distance to our target earthquake. And here we are very surprised to see this very high peak that was around the end of September, as you see from the graph. So more than 1 month before the earthquake, even more or less 2 months before the earthquake, and as you see from the above picture, this was not a large, very big earthquake as magnitude, otherwise you see the jump also here, there was a little higher magnitude, but it was closer to the earthquakes, so this parameter was very high. This is a significant seismicity that preceded the Albania 2019 earthquake. Then this VRE analyzed also the Global Navigation Satellite System GNSS data from also EPOS platform. So the first point is search the GNSS stations that are available in the area. That depends with some, for each country it's not the same. Here there are several stations identified by the VRE. Then it selects the closer to the epicenter and divide for the one that are on the footwall in red and the one on the hanging wall in black. Obviously this is a generic concept because like this one in South Italy are not on the hanging wall of the fault of this earthquake, but they are divided on with respect to the strike of the fault, the one on one side and on the other side. So that's not a geological interpretation of the GNSS station position. That's because we want to try to investigate eventual tectonic variation of the plate movement using stations that are on the transect, the perpendicular direction with respect to the fault direction. So the VRE automatically selects the perpendicular couple of stations underlined by these lines in this map, and then construct the time series and consider also the distance with respect to the epicenter, because we think that the effect eventually related to the preparation phase of the earthquakes can be likely detected by the closer couples of stations. Then and this is done for the northeast and vertical component, the up component of the displacement of the ground recorded by the GNSS network with the weekly time series data. We also have done another type of analysis. In this case the quality is not so good because the number of stations is very little overall in the Albania side. In Italy there is better coverage, so this map are the variation rate of displacement week by week. For every week you see from 4 April 2019, then 11 April 2019 and so on. There is a weekly variation of position, but you see big features that are not so likely to be physical. They could be due more to the lack of a sufficient number of GNSS stations on Albania side. But if you are analyzing an earthquake with a better GNSS coverage, you can find more reliable result. Then we go to the atmosphere analysis with the atmospheric data downloaded from NASA MIRA-2 climatological data. This VRE calculates a multi-year trend and remove from the data, in this case a linear trend. You see the, unfortunately, temperature that from 1980 to 2025 increased of several degrees in this region. The SO2 is decreasing, that's good because this is a pollutant gas. And other parameters that are analyzed by this VRE, and the trend is removed, and these are the multi-year trend after removal of this global warming, or anyway the multi-year trend. After each day is analyzed, and if a parameter is anomalous, is extracted and plotted in this graph with for each line represent one parameter. The first one is SO2. Then there is surface latent heat flux, surface air temperature, humidity, dimethyl sulfide, carbon monoxide, and aerosol. And the next step, we see the cumulative graph of all the anomalous parameters with an interesting acceleration that is about 1 month before the earthquake. That's very interesting. last point is to analyze the swarm satellite data that represent the magnetic field recorded by satellite in the ionosphere at an altitude of about 460-500 km of swarm Bravo, that is little higher. These are 10 tracks of residual. They are shown to check what is going inside the calculus. So then variation of the signal like this one with respect to the track are extracted if they are recorded inside the research area and with geomagnetic quiet condition defined by the ST and AP geomagnetic indices that are pre-downloaded inside the VRE, but you can also update with the notebook for data uploading. This is analyzed. There is a warning, but it's okay. Then the visual cumulative number of swarm magnetic track is provided in this last picture, but after this there is the most important picture of this work, that is the cumulative vision of lithosphere, atmosphere and ionosphere. And now I just a little zoom out to show you better, because the most important of this VRE is this picture, so it's important to see all together this analysis, because it's by the comparison of this free layer that we can then suggest some conclusion to our work. And as you see here, you have a quick tool. So for example, the most evident is this seismicity occurred just before. We notice some also little increase in atmospheric anomalies. That could be also a co-seismic effect of this seismic activity very close to the incoming earthquake in about 2 months. We notice this atmospheric acceleration of anomalies about 1 month before the earthquake. We don't see any particular features in magnetic data, but what is very nice from this environment is that if we want, for example, to see what happens if we select a higher threshold of ionosphere, we can just modify the parameter. We can need to go back to the 100%, and if we go back to the beginning of the section of the ionosphere, I want to show you a trick to go quickly. You can just go to the beginning of the VRE, and then you can use the hyperlink to the direct section. So ionosphere, we click and we are directly go here, and the threshold here is defined at 2.5. Let's see with the threshold of 4.0. Then you run this cell to acquire the new threshold, and we can run again also the cell below. So we can just use the run selected cell and all below. So now it will automatically recalculate the ionospheric anomalies using the new threshold, in this case of 4.0. It is still running because it requires a little of time, but it's very easy, as you see, to modify the several parameters. You can even add more other data, writing the cell, and you can change some parameter to see how the analysis changes. And waiting for the result, I want to say that this tool it's important to have a quick analysis of the earthquake or volcano eruption or another natural or artificial hazard, anthropogenic hazard. But it's better to have a more deep analysis for to discuss the result and check what is going on in this analysis. For example, here it's interesting to see now that there are higher trend of ionospheric anomalies just following an increase of atmospheric analysis. This could be an atmosphere-ionosphere coupling, but before affirming this, more researches are necessary. Finally, I want to thank you for your attention, and I hope you can run this code, run on a lot of different earthquakes, because if the scientific community execute a common environment and research framework, this is just proposed, you can modify freely the code, the provided code, then we have more results, and we hope to understand better the mechanism of lithosphere, atmosphere, ionosphere coupling. Thank you so much for your attention. See you.